Welcome to Succeed in Robotics Level 3 from Oxford University Press. My name is Amie Terblanche. I am the co-author of Succeed in Robotics together with Renier Engelbrecht. I would like to thank Oxford University Press for the opportunity to have created this textbook and the lecturer's guide on Level 3. Succeed in Robotics Level 3 continues on the Level 2 Robotics textbook and aim at getting students ready in the robotics field together with two other subjects, the one called programming and the other EDCR, which is electronics. In January 2024, Robotics Level 3 will start at the TVET colleges. The main subject aim is to develop knowledge in robotics in an inter- and multidisciplinary subject and to give students the tools which involve the components of STEAM. STEAM stands for Science, Technology, Engineering, Art, and Mathematics. The main reason for the increase of robotics as a subject is the link that it has to the fourth industrial revolution, which is in full swing, and the 21st century skills that employers would ask from their workers in the future. This subject will not only give the students the knowledge they need in robotics, but also includes a practical component which they can build and create robots. On the level 2, it was with the Raspberry Pi, and now they are learning it with Arduino. They will also learn how to use a 3D printer, how to print components for their projects, and how to assemble it. Teaching time and offering time. Robotics offers 2 semesters, which spans over a total of 24 weeks, excluding the assessment time. 24 double periods of plus minus an hour and 50 minutes, and 1 single period of 50 minutes is offered. This is 56 hours or plus minus 4.5 hours per week. Of this, 36 hours are instructor-led contact hours, which also includes practical sessions. 18 hours are instructor-led contact hours dedicated to practical tutorials on the PCs with the robots. In addition to this, a further 10 hours per term, which is about 1.5 hours per week, is required from the students to practice on their own. This is needed to reinforce and master practical skills, concepts, and knowledge. Timetabling is open to be individualized according to the different colleges' needs as they see fit. Resources management and budget. Physical resources will require a computer lab that has enough computers for all the students. The server must be of good quality and able to carry all the computers connected to the robotics requirements. It is recommended that all the computers is equipped with robotics equipment to make it easier The computers should be in an L or W shape format in the lab with a external USB hub that is placed on the desk and enough desk space to connect either the Arduino or the Raspberry Pi as needed. All programming in the lab should be kept up to date. The computer lab must also be equipped with good enough Wi-Fi and antivirus so that all the files are protected. Teacher and learning materials must be made available to the students on the network, and software must be maintained. CAD, computer aided design, or fritzing software is also recommended. The reason for this is because the students need to plan and draw their diagrams for the projects on the computer. A good budget should be put together by management of the colleges that will make sure that there is a turnaround time of around 6 PCs every year to be replaced. The reason for this is so that the PCs that get replaced are up to date, because as we know, in all things technology, there is big advancements that's made every year. Raspberry Pi and Arduino kits should be ordered at least a year in advance and should be maintained and equipped. Budget should also be made for damages if this needs to be replaced. Each college will decide individually how they want to maintain the robotics kits. It is recommended that there is a robotics kit per student, but the college can decide on their own if they want each student to buy their own or if they need to use the college's equipment. It is recommended that there is equipment available for the lecturer as well, so that they are able to demonstrate certain things to the students. Topic overview. Succeed in Robotics Level 3 has 6 topics available that is relevant to the robotics field according to DHET requirements. Topic 1, Robotics and Our Lives. Topic 2, 3D Printing. Topic 3, Electronics for Robotics. And this will also have an extra component in Level 3, which is Networks for Robotics. Topic 4, Components of a Robot. Topic 5, Programming. And Topic 6, Practical Robotics. All of these topics link in at different stages with the EDCR and programming subjects. Introduction to Robotics. The introduction of robotics, which is the first module focusing specifically on how robotics is introduced. This is an extension of the Level 2 textbook. In Unit 1.1, we look at robotics as a mixed discipline and all the subjects that come together in the robotics field. Unit 1.2, Mobile Robotics, is quite extensive and looks at the different motors that can be used in robotics, including the different wheels that is necessary. This module concludes Unit 1.3, which is Robotics and the Internet of Things. Specifically looks at all the devices that can be connected to the IoT, Internet of Things, and how each of them plays a role in the robotics field. It also looks at basic programming for IoT devices and the different sending and receiving signals that is available. The module concludes with a module summary. There is also a self-evaluation checklist, which is excellent for the students because they can tick off as they learn all the different areas and knowledge. This helps the students and lecturers to know on what level the student is at the end of this module. Then there is a theory, test your knowledge area, which is specifically created for the lecturer and students to see on what level they are and what is needed for them to evaluate or revise. In Module 2, which is 3D printing, there is a big focus on 3D printers. The Unit 2.1 focuses on 3D printing concepts, technologies, and materials. Different 3D printers are looked at, how they work. There's also advancements in the technology of 3D printing and the different types of materials that can be used in the 3D printer. In Unit 2.2, there is the 3D printing process, which is looked at so that students can learn how to print the projects in such a way that they can use whatever is printed and help them understand how the 3D printer works. There's also a wonderful section on the challenges that could be faced using a 3D printer, how to deal with the challenges and how to solve any problems that can occur. Like for instance, if the printing doesn't come out the way the student wants, or if there is some kind of problem with the printer that it isn't printing, how to fix it. In Unit 2.3, there is specifically a section that looks at the 3D object or artifacts that can be printed. This is an extensive unit that specifically looks at the planning of the 3D object or artifact, how to put it together once it has been printed, but before that, how to plan so that each component can be created with the printer, and then also how to fit them together in such a way that each section fits together perfectly. With this 3D printing unit, the students are not only able to print the artifact or object for their specific project, but they are also trained in such a way that they can anticipate problems that arise when they are printing, which obviously helps with the practical side once the students get to the big practical project that is at the end of the year. This module once again has a self-evaluation checklist, which helps the students to evaluate all the knowledge they've gained from Unit 2.1, which was the 3D printing concepts, technology, and material. Unit 2.2, the 3D printing process and challenges, and for Unit 2.3, the printing of the 3D object or artifact. This helps, obviously, the lecturer as well, because they can see at what level the student is and maybe what knowledge need to be revised. Finally, there's a test your knowledge theory part. In the test your knowledge theory part, it is an informal assessment that the students can take. And once the results are out, the lecturers can also look at what knowledge or theory is missing from the students that they need to reevaluate. This helps to make the project at the end of the year so much better, because when they know what knowledge is missing, it is easier for them to go and add that knowledge. Both the textbooks, both these modules prepare the students in a knowledge and practical way. In the next slide, Renier Engelbrecht will continue.
Thank you, Amie, for completing the first part of our webinar. I'm Mr. Engelbrecht, and I'll be guiding you through the rest of this webinar regarding Robotics Level 3. As you can see on my slideshow, I've got all the learning outcomes which we're going to do, some of the module vocabulary, a starting point, all this for the part of the learning electronics for robotics. Right, let's take a look at it. What we're going to do. So we are going to look at, obviously, what is power, different sources of power which we're going to use, the source of power which we're going to use in robotics, because not all power can be used the same. Right, we're going to look at polarity, differentiate between direct current and alternate current, and which one would be suitable for robots. Define the term amp hours. This is become very significant in our country with load shedding. Differentiate between parallel and series battery and solar panel connections. As I've said, very important in South Africa. Calculate total voltage and amperes of batteries and other power sources, such as solar panels, connected in parallel and or series, and calculate total amp hours of particular configuration of batteries and other power sources, again, such as solar panels. Okay, so this is going to be some of the learning outcomes which we've got. Also define the term cycle in terms of alternating current. We're going to look at hertz. We're going to look at the term root mean square and define the concept of electromotive force. Basic outline and purpose of the following components: the voltage regulator, which is very important, voltage dividers, charge controllers, and inverters. All of these are very important in South Africa now with our load shedding. So these are words, not only buzzwords, but very important words, which we're going to learn about. Differentiate between single-phase AC power, three-phase AC power in terms of the cycles involved. Differentiate also between the concepts of neutral wire and the ground wire. Differentiate between components placed in series, components placed in parallel. Calculate the amperes, the ohms, the volts, power components in different configurations. Vocabulary, what are we going to look at? Power, current, solar panels, of course, hertz, voltage regulator, inverter, sources of power, parallel, voltage, root mean square, voltage divider, neutral wire, polarity, series, alternating current, and electromotive force. Okay, so where we're going to start is that robotics can't really function without electronic components inside them. And that's what, and electricity is what makes the current work. And that's making the robots work. Again, load shedding had a real and almost daily impact on our daily lives, which makes people wonder if robots can be made to function on solar energy and other alternative forms of power. So in this particular chapter, we're going to look at that, which we're going to do, and the implication for robotics. We're going to look at the calculations, how to calculate it, and various concepts of voltage regulators, how to get the power down, how to boost the power, all that type of thing. So that is electronics for robots. In the next one, components for robots. Very interesting. We're going to look at a microcontroller. A microcontroller such as this particular one. I hope you can see it. Called the Arduino R3. And then we've got a small breadboard here with a few components on it and a Bluetooth module hanging around there. So that's what we're going to use in this particular module. We're going to use the Arduino. So we're going to look at the typical uses of a microcontroller, the history of the microcontroller, basic configurations for a microcontroller, typical uses of a microcontroller, similarities and differences between the mainstream microcontrollers, single board computers. In level 2, we did a single board computer. Now we're doing the microcontroller. Specialized features of typical microcontroller boards. Why a standard computer would not be suitable for use of a robotics project and where a microcontroller fit in there. The criteria which is typically used in the selection of a microcontroller for a robotics project. Actuator. That thing that opens up, closes again. That's what we're going to take a look at. Purpose of actuators. Differences between actuators. Various actuators and their application. How are we going to apply them? We're going to look at motors, stepper motors, servo motors, industrial motors, linear actuators, solenoids. We're going to look at them as well. When we're choosing an actuator for a specific job, what are we looking for in that actuator? Motor controller, age breach that we're going to look at, sensors. Oh, we've got so many sensors we're going to look at. Switches, push buttons, pressure sensors, distance sensors, lasers, proximity, infrared, ultrasound. So we're going to look at all of these sensors. The GPS. Here I've got a nice example of a small GPS board, which we can use in our robotics. Environmental sensors. There's so many sensors we're going to look at. It's quite a bit. We're going to see how to select these sensors, determine the sensor requirements for a specific task. So what questions do we need to ask? How do we need to ask these questions? Then combination of these sensors and why and how are we going to achieve that? Incorporate various components, which we studied in level 2 and now in level 3 for the design of artifacts or prototypes. It's going to go a bit further, right? Explain how a typical display component can be used to signal output. Level 2, we only used little LEDs and so forth. Now we're using screens. We're using all other types of output as well. Different display components. A single 7-segment display, we're going to look. 2 LCD, the 16 by 2 LCD displays. 8.8 dot matrix displays. We're going to look at those displays as well. We're going to look at the wireless capabilities of a microcontroller. So we're going to look at both Bluetooth and Wi-Fi. Bidirectional communication between a microcontroller and some other device. And then take all of this data from microcontrollers and able to put them on a web page. We're going to look at that as well. Simple web page. Then that's the difference. So it's the input of components, the output of components, and how to process them. Next slide, which we go programming. What are we going to do here? A lot of things. No robot, no artifact can run without programming. So we're going to take a look at what is a microcontroller. We're going to list different programming languages suitable for microcontroller programming. For those of you that want to know, this is what the microcontroller looks like. This is the Arduino R3, the one which we're going to use in our robotics. Okay, list different software available. We're going to use the Arduino IDE, and we're going to use a derivative of C++ for the Arduino to program with. You should be able to install the applicable software for the microcontroller. You need to be able to explain and upload code to the microcontroller. That's what you should be able to do. Demonstrating an understanding for various commands used to set and get values from various input outputs. So we've got the different pins here where you are going to connect to various devices and input and output those devices on those pins for the Arduino. Open and access applicable microcontroller programming environment, such as the Arduino IDE. You need to be able to design, develop, debug project. You need to be able to include applicable libraries. Over here, I've got a GPS unit. It's got libraries that can communicate with the microcontroller. You need to import this library. Over here, I've got a sensor for humidity and temperature. Again, it needs a library. Here's a Bluetooth module. It needs a library to communicate with the controller. So they are connected to various pins. You need to define those various pins. You need to import the libraries, define the various sensors which we're going to use, and form their code to obtain information or data from them or to send information or data to them. You need to be able to look at global variables, local variables, serial communication. That is very important in this module between the device and other communications such as Bluetooth, such as Wi-Fi, such as a PC, such as a single board computer. Reading the state and sending notifications as applicable as it needs to be. Apply and include basic conditional constructs. We're going to learn about iteration, which is the loop. We're going to learn about selection, which is the if and the switch statements. Depending on the temperature, we're going to have some form of other output. Structures around that, which we're going to do. We're going to look at subroutines, user-defined subroutines, predefined subroutines, functions, the concept of parameter passing between those subroutines, value parameters, variable parameters, how values are interchanged in programming, pass arguments to libraries, and the libraries use those arguments to obtain an answer for us. Connect, as I've showed you, connect directly to the microcontroller pins and design simple prototypes, such as this sketch. This is a sketch. This is what a simple prototype is all about. Developing something like that. Incorporate input components. There are so many sensors using a single board microcontroller. Incorporate different polarized components, positive and negative, as part of a design to facilitate input and output towards solving a problem. Build simple prototypes connected directly to the microcontroller pin. Develop a solution that uses microcontroller and or microprocessor in a combination of the two. Read data from digital inputs. Send answers to digital outputs. Use combinations of input and output components to facilitate data transfer. Implement components such as relays, higher voltages. We're going to look at high voltages, 12 volt voltage, 12 volts, AC. We're going to look at that. So we're going to look at embedded. We're going to look at the IBE, the library UART, SPI, I2C, template code, camel caps. That's what we're going to take a look at. Practical robotics. What are we going to do here? Here we're going to build code, assemble, solder. We're going to do everything. Modify print components. Assemble a kit, either according to instructions or you set up the instructions. Interpret basic designs of a kit or a project. Add and assemble various components of the project. The electronic, the various other components refer to maybe the wheels, the gearbox, all that type of thing. But also do assemble the electronic components. Also apply some soldering where those techniques should be used. Test and calibration. Testing and calibration is so important. Write code in a simulated environment to achieve a particular task. Right, which includes debugging the code, making sure that everything runs properly. Deploy the code to a microcontroller. Test the effectiveness of the code based on the specifications. This is what it's supposed to do. This is your answer. Are the two the same? So test the code. Calibrate sensors. Oh, that's so important. Sensors only work when they calibrated properly. Analyze a given problem in the development of a particular robot, artifact, or prototype. List various components required for the design. That's very important. Demonstrate understanding of these components involved in the design. Then, present a decomposition or set up a part of the physical components required. What is required? Decompose. I need this thing and this thing and this thing. Write out the steps for the required design. Then, before we can go and buy electronic stuff, we need to make sure that we know what we want to do and we know what we want. Design circuit schematic. Either on applicable software, on pen and paper, whatever, but first design it before you need a bill of materials to go and see what you need to buy. Create a new design. Configure the environment in which we're going to import parts that you know. Build the circuit. Rearrange, connect various components. Edit and inspect properties. Build the circuit. Develop the circuit. Develop the code. Move the code to the controller. Finish the design test the artifact, create a manual. We're going to take a look at PCB, SVG, and next on PCB. And then there are obviously projects, which there's going to be. Assessment. This course is a course, and obviously there's going to be assessment around it. We're going to have different types of assessment. As you can see from the slide, there's going to be an internal assessment, which is going to be 50%, and an external assessment, 50%. If we look at the tasks, then we're going to see ICAS counts 50%, ISAT 15%, and the external examination is going to count 35%. That would be for the mark. Right, let's go and take a look at the ICAS tasks. ICAS tasks are as follows. 2 tests, which is going to be 20%. 2 practical assessments, which is going to count 50%. And then 1 internal examination, which is going to count 30%. All of this make up the internal assessment and the weightings for that internal assessment. National assessment and weightings. You will see from this particular slide that both level 2 and level 3 follow similar guidelines. However, we're going to focus today on the level 3. Level 3 consists of 2 papers. Paper 1, which is going to be the theory paper, which is going to be 100 marks for 3 hours. Paper 2 is going to be the design paper, which is 80 marks for 4 hours. Let us take a look at each one in particular. We'll see in paper 1, the theory paper, robotics in our lives is going to be 15%. 3D printing is 15%. Electronics for robots, networks for robots, together count 20%. Component for robots, 25%. Programming, 15%. And practical robotics, 10%. This would be the theory paper, or the percentage aligned for each topic. The design-related paper would be as follows. Robots in our lives, 2%. 3D printing, 5%. Topic 3, which would be electronics and networks, 18%. Components of robots, 20%. Programming, 25%. And practical robotics, 30%. This would consist of an 80-mark paper for 4 hours. This concludes our webinar for Robotics Level 3. I would like to thank Amie. I would like to thank OUP for assisting us in presenting this webinar. Thank you and goodbye.